Welcome to my first attempt at a screen capture lecture. This is about permanent magnets, and this is meant to be viewed following the permanent magnet lab demonstration video and some attempt at answering those questions there. So if you haven't watched it yet, go watch that one and then come on back here. So from that video, a couple things became pretty clear, or should have at least. The first is that most magnets are metal, and we'll talk about each of these in turn. The second is that some metals make better magnets than others. For example, those bolts were very effective, but the little like copper disc thingies were maybe less effective. Third is that magnets can be both created and destroyed. And so you could see this when the first bolt attracted the second bolt. It was acting as though it were a magnet, even though it wasn't a few moments ago. Two bolts touching each other just sitting on the table don't behave magnetically, but once one of them's attached to a magnet, it seems to work as though it itself is a magnet. Now, magnets themselves, these permanent magnets like the bar magnet I was using, can also be created and destroyed. It's just a little more challenging, and we'll talk about both of those things. Point number 4 is that there are always two magnetic poles, and this actually is really important scientifically. It's something that was argued about for a very long time. First off, we're going to talk about point 1 here, which is that most magnets are metal. Now, materials are made of atoms. Those atoms can be portrayed as an electron or a series of electrons, because not all elements only have a single electron, orbiting a center that's made of protons and neutrons. This is just hydrogen. You have an electron here, E, orbiting around a P+, that's the proton electron over here, orbiting around this P+ over here, and that orbit creates a sort of angular momentum that we call the magnetic moment. Now, what you think of as the magnetic moment is the current across the area. So since the electron goes this way, that means that the current is actually going this way, right? And so if you have a current that goes like this, counterclockwise, that means that following the right-hand rule, there is a magnetic moment coming sort of out of the page at you right here. That's what we call a magnetic moment, and that's how magnetization happens in a material. It happens because of this electron motion. So now lots of materials have, all materials have these atoms in them. But not all of them have all of these magnetic moments aligned. So for example, in the first case right up here, right, you get lots of different magnetic moments, but when you add them all together, it basically comes up to a big fat zero. They all cancel out because they're random. But when they're perfectly aligned with each other, what you get is a really big magnetization. And this is how permanent magnets are made, is by having these things sort of all assembled. So as you can see, magnetization comes from electron motion, and so the fact that magnets are metal seems like it's something that might be relevant, right? Metals, we know, are conducting. And so if we move on to point 2 here, some metals are better magnets. We can make this a little more obvious. So if you take a look at a periodic table, you can see that metals are all in this pink area right in the center here. So you got like iron right around here, cobalt, nickel, copper, and zinc. And there's, of course, other metals, right? Here's silver, here's gold. Some of these metals make better magnets. So for example, iron right here makes a really good magnet, and zinc over here is very, very bad at being a magnet. And this has to do with electron orbitals. So flashback to chemistry, if you look at the electrons making up a material. Stuff that's over on this side is dealing with an s orbital. This is s orbitals. Stuff in the middle here is dealing with d orbitals, and stuff over here deals with p orbitals. Now, if you have all of your orbital filled, basically what you get when you add electrons to an orbital is you get, first they'll all add facing sort of one direction. And then, as you add more of these things, D has 5 in the initial add, then the next ones that you add all counter the initial ones. And so, if you've filled an orbital entirely, say this d shell here, if you filled the whole d shell, each single electron in the d shell, all 10 of them, then you actually can't have magnetization because each atom is going to have a total magnetic moment of 0 because you get 5 up plus 5 down equals 0. However, you can then go over to, say, iron here, which has 5 of these things filled plus 1 gone. So we can go ahead and erase. Get rid of this guy, this guy. Right now we got 5 up plus 1 down. You still got 4 up at the end, which means that you can get a very strong magnetic effect. 4 up, right on the edge of the canvas there. So that's important because that means that when you're dealing with copper, you have less magnetic effect per atom than when you're dealing with iron. So copper has 5 up plus 4 down equals 1 up, right? And this is why most metal magnets are made out of iron. Now, actual really strong magnets are usually made out of a combination of metal or ceramic and rare materials. So like manganese here is very effective, as are the rest of these things going down the line here. And there are some combos that you can make that work significantly better than just using plain iron, but it's a place to start. So magnets come from electron motion, and metals make good magnets because they have lots of electrons facing the same way in each atom. So you just have to line up the atoms, right? And you get a magnet. If your atoms aren't lined up well, you don't get a magnet. And if you have stuff where the entire electron shell is filled, you can't get a magnet because each atom doesn't have a magnetic moment to add to it. So, moving on to point number 3. Magnets can be created and destroyed. If we look at a material, you can think of it as just sort of a block of stuff with a bunch of protons in the background and electrons that are able to move a little more. But the difference between materials is that in plastics, for example, those electrons are bound in place. So, for example, right over here, I've drawn these little black dots to indicate that these electrons are pinned down. Now, over here, if you look at the metal, these electrons can actually move around. They've got motion. This goes back to when we were talking about potential wells. The electrons in a magnet sort of rest above these little potential wells, which means they can move freely. This is energy going up, and since this electron has more energy than the potential well, these dips down here, that means that it can just sort of move about the metal as it pleases. And, there's sort of an edge to it, which is the edge of the box. Right? If you look over at the plastic, what you got are these really deep wells, and your electrons sit inside of them. They just sort of hang out here, and they're trapped. They can't move because they don't have enough energy to get out of the wells. So they're pinned in place, and that is why when we bring a magnet near a metal, right, if we introduce a magnetic field over here, magnetic field goes through this, then all these free electrons in here can start to spin around and either oppose that magnetic field or agree with that magnetic field. However, if you impose a magnetic field over on a plastic like this, these electrons are pinned in place. They still can't go anywhere. They're trapped just as they are. So when we took the bolts and we brought a magnet near them, what we did was we just introduced this magnetic field right here. And we caused those free electrons to spin around, which meant that those bolts behaved as though they were magnets. Now, you can take a permanent magnet and actually just destroy it. And the way you do that is you just add heat. So heat introduces something called entropy. This right here, heat, we usually call it Q, introduces entropy, which we call an S. And that just basically means chaos. You add heat to a system, it gives stuff the opportunity to change how it's shaping. And so starting with 3 up, add the heat, you end with 0 total up. Everything sort of cancels out. Alternatively, if you add a magnetic field, you can do this the opposite way. So you can take this plus a magnetic field up plus this little heat over here and get something that is all facing upward. And that's actually how most magnets are made. You put the materials together, you heat them up, you introduce them to another magnetic field, and then you cool them down while the magnetic field is still there. And what you get is something with a strong magnetic field. Now on to point number 4. There are always 2 magnetic poles. Now, first question you probably ask yourself seeing that is why? Well, as we stated earlier, the magnetization of an atom is related to the electron motion, right? Oh God, I need to stop painting on invisible layers. The electron moves around, and as a result, it creates a vector. Now, vectors have an end with no arrow and an end with an arrow. And 2 poles just means that it's represented by a vector. So one end has to be different from the other end because that's what the arrow tip represents. So we just call one of those north, the other one south. And if you stack them on top of each other, you just move that north up a bit, right? North goes up here. And this becomes sort of a 0 magnetic field spot due to the fact that it's right next to a north pole and a south pole. If they have the same strength, your fields add there and they add up to 0. Now, let me just go ahead and erase those bits before I add the next thing. Then we can take a look at what magnetic fields look like around here. So magnetic fields exit a north pole, enter a south pole, and so they're indicated with these arrows as shown here. If you add more magnets together and you have a stronger magnetic field, it gets denser, as shown over here by the fact that there's 3 bits as opposed to over here where there are 2. And the other thing to note is that a magnetic field points in the direction that a compass will point. So if you stick your compass in this magnetic field here where everything's pointing down, B points down, which means that your compass needle will also point down, which in this case would be a magnetic, the geographic north, but a magnetic south pole. The needle of a compass is a north needle, so it points towards the south, which is why, somewhat counterintuitively, the geographic north pole is actually the magnetic south pole. So if you didn't get that right on your lab report, now's a time to go back and correct yourself. Right, so those are all the important points I wanted to go over here. Hopefully this video has been helpful. And of course, if you have feedback, feel free to shoot me an email. This is, of course, my first time doing something like this, and so it could be complete garbage. But I hope it wasn't. I hope it was helpful. And I'll see you during office hours or during class time. Take care.